In this example, we have that Abbott spots a campfire at a bearing of north 42 degrees east from his current position. Now, we have a bearing of north 42 degrees east. The way that we're going to draw that is a little bit different than how you draw angle measures from standard position. What north 42 degrees east means is that we're going to make a point to represent where Abbott currently is standing. I'll use A to represent Abbott. North 42 degrees east means when you face north direction, turn 42 degrees towards east. So face north and turn 42 degrees towards the east direction. That is what a bearing angle measure represents. It is not the same thing as standard position. It's always typically going to be from north or from south, and then turning east or west. Let's look at what else we have. We are told that Costello, who is positioned 2,200 meters due east of Abbott, so I'll draw a line going east of Abbott to where I believe Costello is standing. We determined that the bearing to the fire to be north 31 degrees west from his current position. So from Costello's position, he has a bearing as well that is north 31 degrees west. So I'm going to draw another little coordinate plane at the position for Costello. And from north, turn 31 degrees west. And then that is the direction of the fire. So I have the fire up here. That is where the fire is. What we are trying to do here, it says to determine the distance from the campfire to Abbott, as well as the distance from the campfire to Costello, rounded to the nearest meter. So we're trying to find the distance to Abbott, I'll say that is X, and the distance to Costello, I will say that is Y. Now with this situation, there's some information that we do know for the triangle on the inside. Do note that 42 degrees and 31 degrees are not the angle measures inside the triangle where Abbott and Costello are standing. If we want to find the angle measure inside of this triangle, note that this creates a 90-degree measure. So that angle measure at Abbott's current position should be the complement of the angle measure given from that bearing. So this angle measure here should be 90 degrees minus 42 degrees is 48 degrees. Likewise, the same is true at Costello's position. We have a right angle measure there at Costello's position. And so if we want to find the angle measure on the inside of this triangle here, this should also be the complement of the bearing provided for Costello. So this is 90 degrees minus 31 degrees. That would give me 59 degrees. Not all bearing questions are going to work in that exact manner, but you typically can manipulate the angle measures provided from the bearing to get particular angle measures inside the triangle. Now that's all well and good, we have those pieces of information, but if we have two angle measures inside the triangle, we should already be able to solve for the third one. The angle measure at F, I'll say the angle at F, should be the result of 180 degrees minus those two that we just calculated. Minus 48 degrees and minus 59 degrees. That should give you 73 degrees. So we now have a good amount of information for this triangle. If you want to redraw this to clean up a little bit, if there is too much going on, It's always a good recommendation. We have 48 degrees, we have 73 degrees, and we have 59 degrees, as well as one side length that we know is 2,200 meters. And we are trying to solve for x as well as y. That means we now should be able to use the law of cosines to go forward with this. We now can use the law of cosines because we have an angle measure as well as a side across. So we have one full ratio, and we can use that information to take, say, for example, 48 degrees and solve for the side length across from that, and do the same for 59 degrees. So let's do that. Let's start with 48 degrees, finding the side length across from that, which is y. If I want to solve for y, I will make that with a fraction with y on top, structured so it is divided by sine of the angle measure across from it of 48 degrees. And I'll set that equal to a full ratio of the side length and angle measure that are known, which is 2,200 meters, and sine of 73, the angle measure across from 2,200. All I need to do to get y by itself is multiply sine of 48 degrees over. That will give me y is equal to 2,200 sine of 48 degrees divided by sine of 73 degrees. And with that, I should be able to approximate y. Let's use a calculator for that purpose. Make sure you're in degree mode since we're plugging in 48 degrees. 2,200 times sine of 48 divided by sine of 73. That gives me 1,709.6, or to the nearest meter would be 1,710. The only thing left is to solve for x. Don't be tempted to use Pythagorean theorem, even though we know two side lengths, because Pythagorean theorem only works for a right triangle. Still use law of sines to solve for x here. I'll structure this so that x is divided by sine of the angle measure across from x, which, since we're working with x now, the angle measure across from x is 59 degrees. That's sine of 59. Is equal to, I'll use the same ratio from before, 2,200 meters divided by sine of 73. Meaning when I solve for x, the question is going to look very similar. Instead of 2,200 times sine of 48, this will be 2,200 times sine of 59, and that will be divided by sine of 73. Allowing me to approximate x, the distance from Abbott to the campfire. Again, let's use a calculator to approximate that. That's 2,200 sine of 59 divided by sine of 73 to give us 1,971.9, or to the nearest whole meter, 1,972. Note that this question, again, is not working with a triangle that is a side-side angle triangle, so we do not need to be worried about ambiguous cases. We also, if you notice, we're not forced to use arcsine in any part of this solution. So it's another reason why we're not really worried about having another possibility for this case. In this situation, we just have our two answers for 1,972 meters and 1,710 meters.